Okay, cool. I think we should get started. We have a lot to cover today on a very exciting topic that's critically important. But for students who are taking the class at ETH, this is a topic that we cover, but I'm not planning to test you on it basically, and you can see it from the past exams also. But this is really for your benefit, and it's really important to learn about timing and verification, because in the end, it turns out verification by itself is the most time-consuming and the most expensive process in designing a working computing system. It's really all about verification. You spend a lot of time in design, yes, but in today's systems, more than 60–70% of the time is spent on verification and testing and making sure the thing really works. And if you include the testing that's done during the design stage, actually, that fraction is even higher than 70–80%. Okay, so that's the importance of this lecture, basically. And I'm going to skip the required reading, so hopefully you know these. We discussed this yesterday. So next week, we're going to go up one level. We're going to start with the microarchitecture and ISA, actually. Actually, we're going to start with the ISA, instruction set architecture first, talk about the von Neumann model and programming, and then we're going to jump into microarchitecture. So we're going to switch gears a little bit. We're going to go up in the stack. And you remember the required assignments, so I'm going to skip those also. So this is the agenda for today. Basically, I plan to wrap up finite state machines. Oh, wait a second. I hear myself. Okay, I had to close the YouTube window. Okay, basically, I'm going to wrap up FSMs and Verilog. This is going to take really short time because we really covered essentially everything that you need to know to build finite state machines in hardware description language and Verilog. And then we're going to jump into timing and combinational circuits, and then in sequential circuits, and then we're going to wrap up with a lot of discussion on circuit verification, and also doing test benches in Verilog and how to test your circuits in Verilog. So that part is going to be important in your labs, for example, because you're all going to do labs and test your circuits. Okay, so let's do this wrap up quickly. Recall that we covered finite state machines in lecture 6, and a finite state machine consists of 3 parts. You have the next state logic that determines what is your next state. You have the state register that we talked about, D flip-flop, for example, that stores your state. And then you have the output logic also that determines what the outputs are. Essentially, you have the state register, and you basically update the next state in the state register using the next state logic. And essentially, this consists of both sequential circuits and combinational circuits, as you know already. Sequential circuits is the state register, and the combinational circuits is the next state logic and the output logic. You've seen this before. And we've already seen how to do all of these in hardware description languages. So we're going to put things together in a little bit, but with one example, and I'm going to leave the other example for you. So the first example is something we're going to cover in timing a lot, basically clock. You already know about the clock. And there might be reasons why you may want to divide the clock frequency by 3, for example, so that you operate with a slower clock, depending on your requirements. So this is what that means, basically. You have a clock that looks like this, and Y is the clock frequency, clock divided by 3. Essentially, the output, at least in this case, what does it mean to divide the clock by 3? It means that the output Y is high for 1 clock cycle out of every 3. In other words, the output divides the frequency of the clock by 3, essentially. And basically, to be able to do that, this is how we design the finite state machine, basically. It's not that difficult. As you can see, you have 3 states, S0, S1, and S2. And in S0, and in each state, you stay the same amount of time, clock. So clock transitions from state to state. But S0, in S0, Y is equal to 1. In all other states, Y is equal to 0. Okay, that's the idea. So you can see that the Y output is the output of the state machine, and you transition on the clock edge, rising clock edge. And this is the finite state machine to be able to do that for. So we're going to define this. So you have an input clock, it's resettable, and then you have an output Q in this case. And we have a state and next state, as you can see. We need 2 bits for that because we have 3 states. And then we use parameters to define the state so that it's more readable, S0, S1, S2. But these really correspond to state encodings, as we discussed in lecture 6. As I already said, this state and next state are 2-bit regs, not registers, as we discussed last time. And the parameter descriptions are optional, but it makes reading easier. And this is your state register, as you can see. So basically, state gets next state every positive edge of the clock. And then there's a reset signal that happens. That's basically resets the state to S0, as you can see over here. Okay, that's easy, as you can see. It's sensitive to only clock and reset is active when it's 1. And it's an asynchronous reset, if you remember from the last lecture. And next state logic is very easy also. Basically, this happens at any input change, as we discussed last time. And you basically switch based on the state. If state is S0, next state is S1. If the current state is S1, next state is S2. And if it's S2, next state is S0. And then there's a default case that may help you with debugging, for example, potentially. Right? Okay, and then output logic is also very simple. Basically, the output is 1 only if the state is equal to 0, as you can see over here. So basically, we created a very simple finite state machine in Verilog. And in this case, output depends on state. So it's a Moore type FSM, if you remember from lecture 6. So this is the entire finite state machine in Verilog, basically, that contains the state register over here, the next state logic, and the output logic. So you can see that the output logic is very simple, depending on the state. Okay, so basically, we know how to build finite state machines, but I mean, you knew that before. We just put everything together from the last lecture here. And I'm not going to cover this one. You remember the smiling snail from our lecture 6 also. We designed the finite state machine for this. In fact, we designed the Boolean equations for this. I'm not going to do that at this point, but essentially, you can also write it in Verilog, and I'll let you study it. It's very similar to what we have just discussed. It's not that different, basically. And the entire finite state machine, this is a Mealy type finite state machine, but the entire finite state machine looks like this. But it's, again, very simple. You can see that even the state transitions are very simple because these are really simple finite state machines. Later on, not next week, but the week after that, we're going to see the finite state machine of an entire microprocessor, the little computer 3D microprocessor. And you will see that that finite state machine is much bigger. And there's a lot more going on. And writing that in Verilog is going to consume more Verilog code for you. Okay, so this is basically what we learned in the last part of last lecture. We described sequential circuits. We talked about the always statement. This is needed for defining memorizing elements like flip-flops and latches. But it can also be used to define combinational circuits. And sometimes it's much easier to define combinational circuits using always statements, as we have seen. But sometimes it's not a good idea to use always statements to otherwise easy to describe combinational circuits. We talked about blocking and non-blocking statements. So hopefully you remember that. Blocking, non-blocking, blocking. Essentially, these are useful for implementing state transitions at the end of a block, right? That's why you use these less than or equal to assignment over here. That happens at the end of the block. Okay, and then we talked about describing FSMs in Verilog just now. So to put everything together. So now we're done with essentially hardware description languages. Of course, you will learn a lot more when you do the labs. And the best way of learning a hardware description language, or any language for that matter, is really by doing practice and writing code, looking at code, debugging code, and understanding how things work through that practical approach. And that's why we have the labs in this class. Okay, so that was the wrap up from last lecture. Now let's go into timing and verification, which I said is a fascinating topic. So this is what we will cover. We'll cover timing in combinational circuits, essentially short path and long path delays, as well as propagation and contamination delays, which affect the short path and long path delays. We'll briefly talk about glitches, why they may matter, they may not matter. Then we'll talk about timing in sequential circuits, define setup time and hold time, and determine how fast a circuit can operate in sequential circuits. We'll talk about the sequencing overhead, for example, due to flip-flops and latching. And then we will switch to circuit verification, talk about different ways of making sure a circuit works correctly. And we'll talk about two different types of verification, functional and timing. And as I said, these are critically important because in the end, you need to make sure your circuit works. And so far, we've assumed that timing doesn't play into our decisions, but timing is essential. Everything has a delay, and we need to take that into account. Okay, let me give you the bigger picture to begin with. Basically, circuit design is really a trade-off between multiple different metrics. Area, clearly, we discussed, right? Circuit area is proportional to the cost of the device, and ideally, we would like to minimize the area. That's why we have the logic minimization techniques. Speed and throughput. Ideally, we want faster, more capable circuits to solve the most difficult problems relatively quickly, as we discussed in the first lecture. And power and energy. Clearly, this is true in almost all aspects of computing, but especially in mobile devices, we have a very limited power supply and we have a limited battery. So we would like to minimize the energy and power consumption that we have in our circuits. And even high performance devices are limited by the power that you can supply to these very high performance devices, and you have and they're limited by cooling as well. And also you have the design time, which is important, as we discussed at the beginning of this lecture. Clearly design, I should call this design and verification time. Designers and verifiers are expensive in terms of time and money, and if you are too late in designing and verifying and putting out your circuit to market, the competition may already have surpassed you. So this is really important as well. So all of your efforts would be useless if you're not fast enough, quick enough, basically. And requirements and goals clearly depend on the application, and there are many, many applications. But if you're good at all of these, clearly you're very competitive, even if your application is very specific to something, right? Okay, so we'll talk about circuit timing. Until now, we talked about functionality of circuits, right? In fact, some of you asked questions in the last lecture related to timing, and I said that let's defer that until later, which is today. So basically, so far we concerned ourselves with the logical functionality, but timing is also a critical component of a circuit. How fast is the circuit? How fast can we get the output after we apply the inputs? That's what this means, basically. How can we make it faster, if it's possible? And what happens if we run a circuit too fast? Will we get errors, or will we run into other issues, like maybe burning down the circuit, right? So a design that is logically correct can still fail because of real-world implementation issues like this, and timing is one of them, basically. So in the first part of this lecture, we're going to talk about combinational circuits, combinational logic timing, essentially. And we're going to break this abstraction. Digital logic we have is a convenient abstraction, and so far we've considered it as the output changing immediately with the input changing, right? So we have this inverter that has an output Y, input A, and we assume that the output Y changes immediately after A changes. So clearly this is not real. This is not correct. This is just an abstraction. It's also called a functional or logical abstraction. But in real life, you have a delay between the output and the input. So after you apply the input, there's some time it takes for the inputs to propagate over the wires, plus go through this inverter that I showed you earlier. And transistors take a finite amount of time to switch. And this is the example. Ignore the wire delays for now over here. This is the inverter delay that we see over here. And clearly, there's some time difference until when the output Y becomes stable, or let's say large enough, logical one, let's say. And that's the delay of this inverter, if you will. And there are different definitions of the delay potentially, right? If you go into the analog part, you can say basically the 50% point of the let's say voltage. When do you get to the 50% point? That could be delay, but it could be from the 10% point over here to 90% point over here also, and the analog range of the voltage that you apply to the circuit. You don't need to worry about that at this point. You just need to worry about that there's a specified delay, and the delay is specified as a maximum delay. There is a maximum delay of this inverter, and there's also a minimum delay of this inverter, and we will see why both of them are important. Okay, so this is an example from a scientific paper that talks about, that basically simulates an inverter and shows a real delay example. So here, for example, the 90% high input leads to a 10% low over here, and the delay is, as you can see, 0.175 nanoseconds. So there's some, after the input is applied, you get a delay. After the input is applied here, you also get a delay over here, as you can see. And this is the 50% to 50% delay, as I mentioned, and this is the 90% to 10% delay, as I mentioned over here. And you can define different delays. We're not going to talk about that, but this is real, basically. In circuits, you have delays. So, okay, let's talk about this delay a little bit more. So this is fundamental. It's really caused by the capacitance and the resistance in a circuit. And also the finite speed of light. Basically, you cannot move the electrons or the holes faster than the speed of light, essentially. So wires have delay as well. So anything affecting these quantities can also change the delay. For example, the rising edges or the falling edges of the inputs. That's certainly possible. That have an effect on the delay, whether you're on the rising input or the falling input. So rising means we've already discussed this, but let me go back here. So here A is rising, right, going from 0 to 1, and Y is rising over here also. Okay, and different inputs have different delays also because they may have different paths. Changes in environments like temperature may actually lead to delays, as we will also discuss. And aging of the circuit may actually change the structure of the circuit and may actually change the delays in the circuit. So there's a lot of effects going on. As you have used your computer for 20 years or 30 years, that may become slower also potentially because of the delays, because of the circuit level, device level structural changes, which we're not going to talk about in this lecture clearly. But we're going to abstract. Basically, we have a range of possible delays from input to output. We're going to abstract everything as a minimum delay of the circuit and a maximum delay of the circuit. Okay, so for this, let's define some, at least combinational delay terminology. So we're going to look at the delays from an input to output, and output will be labeled as Y. So contamination delay, TCD, is the delay until output starts changing, and propagation delay is the delay until output is stable, basically, finishes changing. So you can think of contamination delay as the shortest possible delay and propagation delay as the longest possible delay for a given circuit, let's say. So let's take a look at this combinational circuit. It has two inputs, A, B, and an output Y. It's combination logic, as you can see over here. So if you change input A, so it could be going from 0 to 1 or 1 to 0. That's what the signal over here means. There is a point when Y starts changing. Y starts basically changing. And that distance in time from A changing and Y starting changing is called the contamination delay. And that's the shortest possible delay. Basically, that means that at this point, your Y may change. Okay, let's take a look at the propagation delay. After A starts changing, Y becomes stable after some point. So that's the longest possible delay needed for Y to become stable at the end of this combinational logic. That's called the propagation delay. So these are important because this is the longest possible delay, and contamination delay is the shortest possible delay in the circuit. So you may wonder, why do I care about the shortest possible delay? It will become clear later on. Don't worry about it now. But clearly, longest possible delay you care about, right? Because if it's too long, then you may have problems in your speed of your circuit, right? You may not get your output in the amount of time that you really want to get your output in. But shortest possible delay also has an importance, as we will see in a little bit. Okay, cross-hatching value, cross-hatching in this here means the value is changing. In a sense, the value is not stable yet. So metastability is part of the cross-hatching, but we don't have a stable output over there. Okay, so we're going to calculate longest and shortest delay paths in combinational logic. And we care about both of them, as I said, and we will see why about the shortest path later. Longest path is hopefully intuitive, but maybe not in the same way as I will describe it later when we come to sequential logic. So when we come to sequential logic, all of these paths will become even more clear. Okay, but this is an illustration of a circuit with 4 inputs and 1 output, as you can see, 2 AND gates and 1 OR gate. And you can see there's a short path over here, which goes through only 1 gate. The input goes through only 1 gate to affect the output. And there's a critical path, which is the longest path, which goes through 1, 2, 3 gates, right? In this case, we can consider that the critical path because you really exercise all 3 gates for A and B to affect output Y, right? Okay, so let's take a look at the delays in terms of the gate delay. So propagation delay, which is the longest path through this combination logic, is 2 propagation delays of the AND gates. Because we have 2 AND gates, we multiply the propagation delay of the AND gate by 2. They're the same AND gate. Plus, and add to it the propagation delay of the OR gate. So hopefully this is trivial, right? You basically add up the delays of the gates that are on the critical path, essentially. Shortest path, again, what is the shortest path here? It goes from input D to output Y through this gate. And there's only 1 gate, that's the AND gate. So we take the contamination delay, minimum delay of this AND gate. So the minimum delay through the circuit is the contamination delay, or minimum delay of the circuit is the contamination delay of only the AND gate. Okay, so hopefully that's clear. And this is from your book. Basically, this shows how things propagate. So if you, for example, change A from 1 to 0, it takes time for N1 to change, as you can see over here. And then after N1 changes, it takes time for N2 to change. And then after N2 changes, it takes time for Y to change. That's why you get 2 AND gate delays plus 1 OR gate delay. Hopefully that's obvious. Note that not all changes in the input affect the output. In this case, we constructed the input such that going from 1 to 0 actually changes the output from 1 to 0. But sometimes actually it may not, right? So if this were a 1, if C was a 1, for example, going from 1 to 0 would not matter at all, right? Because output will not change, okay? So keep that in mind. So to be able to really exercise the worst case delays, you really need to exercise the worst case inputs. Okay, and the shortest path, which is the best case delay, in this case, is really when D changes, as you can see, from 1 to 0 here, and Y also changes from 1 to 0. So it basically takes this AND gate to change. And it's really the minimum delay of that AND gate, which is the contamination delay. So we're not going to go into how we calculate the delay for every single gate. That's below the abstraction level of this course. So again, if you're really interested in that, it's fascinating also. You should really take a microelectronics design course or semiconductor devices course, for example, that talks about how to calculate delays of these different transistors and also gates built from transistors. But we're going to assume that these propagation delays and contamination delays are given to us from a cell library, for example, right? And that's our assumption. We're going to use that abstraction to calculate our circuit delays. Okay, so and how is it given to us? Basically, they're given to us based on specification. So this is one specification. This is, again, TTL, transistor to transistor logic. As you can see, this is all type of things that you put on your breadboards, for example, to do design. But this is no different from a cell level library, except you can visualize this one. You can see that this has 4 2-input NAND gates, which is a NAND 2 gate. And basically, the specification of this part says the typical delay at 25 degrees Celsius is this much, right? At some voltage. The highest voltage, it leads to lowest delay, as we discussed earlier when we talked about power also. You can see that the typical delay is, I think it's 7 in terms of nanoseconds, I believe. It doesn't say over here, but it needs to be said somewhere clearly. But the max delay, as you can see over here, is 135 nanoseconds. So basically, typically, you get this propagation and contamination delays. In this case, contamination delay is not provided. Perhaps it's 0. I don't know. You have to look at other parts. Well, this is just the propagation delay, as you can see. Contamination delay, you need to look at some other row. Sorry about that. But you can see that even the propagation delay has a minimum and maximum. Okay, so there's heavy dependence on voltage and temperature. So depending on at what voltage and temperature you're running your circuit, you really need to make sure your circuit works, right? And there's a huge dependence over here, as you can see, 7 to 135. But basically, someone specifies these propagation delays and contamination delays for us. Hopefully, they optimize a circuit. Okay, so let's take a look at an example worst case propagation delay, which is the worst case delay critical path of a circuit. And we're going to look at the 4-to-1 multiplexer that we discussed multiple times in the past lectures. And we're going to look at 2 different implementations, actually 3 different implementations of it, but I'm not going to discuss the third implementation as much, and that's going to be the best one. But let's take a look at 2 different implementations of it first. So let's assume that we're using a library with these gate delays. I'm not going to go through all of these, but a lot of these make sense. So 4-input OR is, for example, 90 picoseconds. 30-input NOT is, an inverter is essentially 30 picoseconds, which makes sense, hopefully. And then you can see that we're going to use also tri-states in some of the designs. So this is the first implementation that does not use tri-state buffers. You can see this is a 4-to-1 multiplexer that we constructed before. It's used, it's designed using 2-level logic, which is AND gates followed by an OR of the output of the AND gates. And you can see that some of the inputs are inverted to some of the gates as they should be, right? So if you're selecting D0, for example, both of these should be 0, and they're connected that way. So let's take a look at the propagation delay, the critical path delay of this implementation of the 4-to-1 multiplexer. So there are 2 things we need to look at over here. One is the propagation delay from the select signal to output. Output is always considered Y. That's why this is select to Y over here. And the other is the propagation delay from the data signal to the output. So we want to calculate both because there could be two possible paths that could be critical in this case. One is from the select signals, one is from the data signals to the output. Let's take a look at the propagation delay from the select to output. Basically, select signal, and both of them are actually the same in this case in terms of the gate delays they induce. Let's take a look at S1, for example, but S2 is essentially the same. S1 goes to one inverter, and then one 3-input AND gate, and then one 4-input OR gate. So basically, the propagation delay from select to Y is the propagation delay of a single inverter, one 3-input AND gate, and one 4-input OR gate, which means that you basically look up these 30, 80, and 90 and sum them up. That's 200 picoseconds. Okay. And the second is, as you can see, propagation delay from D to Y. Again, all of the Ds go through the same delays, same gates. So let's pick one. From D0, for example, you go through one 3-input AND gate and one 4-input OR gate. So that's strictly less than the propagation delay from select to Y, as you can see, as expected also. So basically, that's 170 picoseconds. So really, the propagation delay, overall propagation delay of this, the worst case delay of this multiplexer is 200 picoseconds. Okay, let's take a look at a different implementation that uses some AND gates and some tri-state buffers. Essentially, AND gates are used to drive the select signals or enable signals of the tri-state buffers, as we discussed. So somebody asked, wouldn't we have to consider wire delay? Absolutely. You need to consider the wire delay also. In all this I'm doing, the assumption is that wire delay is 0. But in real life, you may need to consider it, certainly. So that's a very good question. We're going to ignore the wire delays in this lecture, but the issue is actually more complicated, as you mentioned. Okay, so let's take a look at this second implementation. In the second implementation, as I said, we're going to select we're going to use tri-state buffers, and the enable signals of the tri-state buffers will be essentially the outputs of the AND gates, which are determined by the select signals over here. So again, there are two paths. One is select to output, and the other is data to output. And clearly, data to output is going to be small in this case. So let's calculate the data to output first. Basically, in order to go from any data input value to output value, you go through only one gate, which is really the tri-state buffer, right? And that's the propagation delay of that is only, well, there are two specifications you can see for the tri-state buffer, data to Y and then enable to Y. We're exercising data to Y, which is 50 over here. So the worst case delay from data input to output is 50 picoseconds. But the worst case delay from select input to output is one inverter, as you can see, one 2-input AND gate, and then one tri-state buffer from the enable signal to the output. And that gives us one inverter delay, 30 picoseconds, plus one 2-input AND gate, 60 picoseconds, and one tri-state buffer from enable to output, which is 35 picoseconds. That's 125 picoseconds. You can see that this design has a worst case propagation delay of 125 picoseconds, which is much better than the 200 picoseconds on the design over here on the left. Because we've eliminated the large gates, if you will, right? We don't have a huge, well, 4-input OR. We don't have 3-input ANDs over here. We basically replace them with tri-state buffers and, as you can see over here, the 2-input AND gates. And again, we're not taking into account wire delay. If you actually take into account wire delay, the loading may be higher in some of these. But again, we're not going to deal with that at this point. But still, 125 is much lower than 200 picoseconds, as you can see. Okay, so this basically clearly shows you that two different logic level implementations of the same functional circuit, same Boolean equation, let's say, gives you completely different delays. Okay, and we've already said that. And again, the worst case delay, you need to take the worst propagation delay, worst case propagation delay, which is 200 picoseconds in this case and 125 picoseconds in this case. Okay, so this is a third 4-to-1 mux implementation. And this is actually better than either of those, as you can see. And this is completely based on tri-state buffers. As you can see, this is a 2-to-1 mux, this is a 2-to-1 mux, and this is another 2-to-1 mux. And each of them is essentially the same. And each of them is based on tri-state buffers, which we have seen in the past also. If you do the calculation over here, basically, the select to Y delay, select 0 to Y delay is really 85 nanoseconds. And any data to Y delay is 100 nanoseconds. And as a result, this is actually faster, if you will. Okay, this is nanoseconds and the other picoseconds because I actually copied it from a different edition of the book over here. So you can imagine that these are also picoseconds, right? It's otherwise the rest is the same. Okay, so you can see now the third implementation is even better, right? Okay, so let's talk about calculating long and short paths. It's actually not always this easy to determine the long and short paths. I made it a bit easy. Not all input transitions affect the output. You can have multiple different paths from an input to output. We kind of have two paths over here, but what if you imagine having a more complicated combinational logic that has 100 different possible paths or 1,000 different possible paths from input to output? These are usually large circuits, clearly. Now, it may not be easy to figure out what is the longest path and what is the shortest path in this case. And circuits are also not all built equally. Different instances of the same gates may have different delays, especially after you manufacture them. They're subject to manufacturing variation. Wires also have non-zero delay. It increases with length and loading on the wire. And temperature and voltage affect circuit speeds, as we discussed earlier. Not all circuit elements are affected the same way. This can even change the critical path of a circuit. So if imagine you have 1,000 different potential critical paths in a combinational logic, and when you change the temperature, different gates and different paths get affected very differently from each other. And even though at 25 degrees Celsius, one path may be the longest path, at 85 degrees Celsius, some other path may be the longest path. So now you have a dilemma, basically, right? Which one is your longest path? How do you determine your longest delay? Do you really take the worst case into account, which is operating at, let's say, 125 degrees Celsius, the circuit, and operating at the highest level of manufacturing variation? Those tend to be usually very, very conservative. So this is actually not easy to determine the long and short paths. All of them have solutions and trade-offs, but we're not going to go into how to solve those issues. You may actually clearly at different levels of temperature, you may actually run at different frequencies, right? A circuit. You may say, okay, at 125 degrees Celsius, my delays are very long in some of these paths. As a result, I cannot run the circuit at very high frequency, as we will discuss in a little bit. So I'm going to use a much lower clock frequency for my chip. At 25 degrees Celsius, on the other end, my delays are relatively short, and I know the critical path is this, so I can run the circuit at a much higher frequency. Okay, so we will see that in a little bit when we talk about sequential logic, but I wanted to inject this right now because temperature may really affect your clock frequency at which you run the circuit. And that's one way of solving the problem, right? Otherwise, you always run your circuit at the worst possible delay, right? Which is at the highest possible temperatures delay. But that may not be a good idea if most of the time you're running your processor at 20 degrees Celsius, right? Okay. So designers usually assume worst case conditions and run many statistical simulations to balance yield and performance. So this is actually a lot of art and simulation and statistical simulation. So I'm not going to go into exactly how these paths are determined, but what I showed you is a good back of the envelope calculation of these paths. And then you can also add some margin saying that, okay, the rest will take this amount of time based on my measurements, and then you add that margin on top of the delay. For example, that way you can take into account the wire delays that you have in the circuit. Okay, so let me summarize the combinational timing. Circuit outputs change sometime after the inputs change. This is caused by finite speed of light, and delays depend on inputs, environmental state, voltage, temperature, etc. And we discussed two notions of delay. Contamination delay leads to minimum possible delay from input to output, and propagation delay leads to maximum possible delay from input to output. And delays change with many different things like circuit design, operating conditions, and manufacturing variation as well. Let me quickly talk about output glitches. I don't want to spend a lot of time on this one because when we see the sequential timing later on, this may not matter. In general, output glitches don't matter. It's good to be aware of them, though, as a designer, because when you see some output changing for a very brief amount of time, you would like to know why that is, and you would also like to make sure that that's not a problem, right? So from that, if you design your circuit nicely, these glitches should not matter. Only time they may matter is if you don't design your circuit nicely, or you actually push your clock frequency very, very high, and as a result, you may actually capture something that is glitching. Okay, so what's a glitch? Basically, glitch is one input transition causes multiple output transitions. So let's take a look at the circuit. This is the initial state of this interesting circuit, let's say. You can see that the result is 1 with these inputs applied to it. But let's assume that we go from 1 to 0. as opposed to staying at 0. Now, if you actually do that, what happens is there are two paths that are really affecting your output, right? One path is initially, if you're 1, that means that this is 1. So this path is also this path is changing from 1 to 0, and this path is also changing from let's say this was 0. So this path is changing from 0 to 1, right? So if the fast path changes faster, it might be that your output may go from 1 to 0 briefly and then to 1 again. So basically, what happens if this changes from 1 to 0, this path quickly changes, and then the output becomes 0 for a short amount of time. And then the slow path changes a little bit later. It basically, what the fast path does is this fast path puts the circuit back to 0 because both of them are 0. And then soon after that, the slow path evaluates to 1, and this becomes a 1 again. So there's a period of time where the output remains a 0 for a short time, because this fast path changes the output more quickly than the slow path can. That's the idea of a glitch. So you may actually briefly get a 0 output over here for some time, even though at some point the circuit settles to 1 because the slow path actually catches up and evaluates, right? And that's the idea, basically. I've already shown you that. And if you actually look at the timing diagram, it looks this way. Basically, B changes. When B changes, N2 changes faster than N1, because you can clearly see that there's only 1 gate over here. There are 2 gates over here. And then because of that, there's a glitch for some amount of time. But then the glitch goes back to 1 after N1 also changes, as you can see over here. So for this amount of time, you have some glitch in the output. Now, this doesn't matter if you don't do anything with this output in the glitch. Make sense? If basically you don't sample this and put it into a latch, for example, put it into a flip-flop, then maybe you don't care about this, right? But this may matter if you actually sample at this point and put it into a sequential logic flip-flop, as we will see in a little bit. So basically, whether or not this glitch matters is really dependent on what you do with the output signal and when you do something to the output signal. So if you actually designed your circuit such that you actually sample the data at the time it is glitching, bad idea, right? Then you actually have a problem. Actually, it's a problem because you really didn't calculate the maximum propagation delay in your circuit very well. You didn't take into account the slow path, right? So you need to take into account your slow path. So if you take into account your worst case conditions and slow paths, these glitches should normally not matter. But again, that's a general rule that doesn't always apply. It really depends on what the designer does with the output signal. Okay, so basically you can avoid these glitches. I'm not going to talk about exactly how you avoid them, but well, I am going to talk about them briefly. But basically by adding some additional circuitry that ensures that a fast path doesn't cause a glitch in the output is the way to avoid these. The question is, how do you add them? So the reason this happens is really you don't have redundancy in the circuit. So if you had another term over here that changes based on B, and that ensures that no fast path can cause this glitch, then you're actually solved the problem. Basically, you can actually design a circuit that doesn't glitch. That's what I mean by what I said. But to be able to do that, you need to add some other function of the inputs as part of another input to the OR gate. So that becomes a 3-input OR gate. Of course, it's not very desirable, and as a result, you may avoid the glitch, but now your area increases. So if these glitches are not a problem in your design, and make sure they're not a problem in your design, then I wouldn't worry about them. But you need to make sure that you don't create the problem of glitches by using a glitching output in somewhere that's important. Okay, so we did not cover K-maps, Karnaugh maps, as I mentioned that they were optional. But very quickly, these glitches can be visible in your truth table, let's say. So Karnaugh maps is one example of a truth table, basically. This is A, B, C, and Y is the output. So this is one way of visualizing the output. AB is 0, 0, AB is 0, 1, AB is 1, 1, AB is 1, 0 over here, and then C is 0, 1. And this is the function, output function over here, that is essentially the truth table for the circuit. And you can see that this circuit really implements A bar, B bar, or BC. Now, the problem is when you move from, when you change B from 1 to 0, there is no redundancy here to ensure that you don't glitch. So to be able to fix this glitch, you add another term, which is essentially considering this part. So don't worry about the K-maps over here. And if you're really worried about the K-maps, take a look at the lecture that I mentioned earlier when we talked about logic minimization. But the solution is really adding one more term like this. Whether you do it through the K-maps or through your Boolean equations, doesn't matter. In this case, the slides talk about K-maps, but I'm not going to talk about them. But basically, we ensure that there's a no transition between different prime implicants. If you remember, implicants are these. Prime implicants are implicants that actually are not reducible, are not eliminatable between each other. But basically, we add a redundant term that could easily be eliminated if you want to minimize a circuit. But we add this redundant term to make sure that the output is not dependent on B. And now we've eliminated that glitching, if you see over here. So even though B changes, Y never glitches because of this redundant term. Okay, so hopefully that's clear. But of course, this is not desirable, right? Now we added one more gate, and we clearly made this a 3-input OR gate. So we increased the area and power requirements of the circuit. So the question is, do we always care about glitches? I already said this, basically. Fixing glitches is undesirable. More design effort, more area, more power consumption. And the circuit is eventually guaranteed to converge to the right value regardless of glitchiness, except if you do the wrong thing with a glitching output, right? And the wrong thing is basically latching that glitching output, for example, to somewhere you care about. So basically, we don't always care about glitches if we have a good design. If we care about the long-term steady-state output, and if we actually calculate our delays correctly, we can safely ignore glitches because we calculate our delays correctly, such that even though the output may be glitching for a while, we're not going to use the output while it's glitching, right? And again, it's up to the designer to decide if glitches matter in their application when examining for example, one important place where this matters is when you're debugging your circuits and when you're examining your simulation output. It's important that you recognize the glitches, because if you don't recognize the glitches, then you may actually think, oh, something wrong is happening, right? So I would recommend understanding glitches from that perspective. Okay, so there's one question. Can we just put 2 buffers in front of N2 to fix that glitch? I mean, maybe your solution is similar to what is described over here. I don't know what the N2 is over here, but yeah. So yeah, okay, basically what you're saying is basically try to make sure that the delays are equalized, right? Yes, possibly, but then you need to be very careful in terms of how you equalize the delays, and it's usually not so easy to equalize the delays, basically. You may still reduce the glitch, but you may not be able to get rid of the glitch. So the best way of fixing the glitch is really adding some terms to the Boolean equation such that you don't even get the glitch in the output. And these are redundant terms, clearly, that makes the circuit suboptimal in terms of the size. Okay, now let me go into sequential circuit timing, and we'll take a break, I think, somewhere in the middle or after the sequential circuit timing. But I want to cover sequential circuit timing now that we've covered combinational timing, because it follows directly from combinational timing. We're going to make use of the combinational timing in the sequential time. By the way, that's a very good question. The 2 buffers, equalizing the delays may potentially be attractive, but they may not always be easily possible. Okay, so recall the D flip-flop. Flip-flop samples D at the active or rising clock edge, and it outputs a sampled value of Q, value to Q. Essentially, it stores a sampled value until the next active clock edge, right? And this is our abstraction. But we also know that the flip-flop is made from combinational elements, right? And we gave one example of a flip-flop. There are many different implementations of a D flip-flop, actually, which did not really cover internally. But all of these, D, Q, and clock, all have timing requirements. And that's the essence of sequential time. So let's take a look at the D flip-flop input timing constraints. Let's take a look at this, basically. So the clock, essentially, clock rises. There's an active clock edge. And while the clock rises, the D input must be stable. Essentially, while the clock is rising, it's being sampled. During the sampling time, this D input must be stable. So what is the sampling time? The sampling time is also called the aperture time. If you're used to photography, for example, aperture time is the time during which the camera lens should be open, right? And stable also. During that time, you're capturing the image. Essentially, here we're capturing the value that is at the input. But it takes some time, basically. D needs to be stable for some time before the clock starts rising. and sometime after the clock starts rising. So why does this happen? Because of the internal design of the D flip-flop. Because internally, you're using there's some sampling mechanism that takes D and propagates it to Q, right? And that takes time, as we have seen in one implementation of the D flip-flop in lecture 6. You have a stage 1 master latch, stage 2 slave latch, and it takes time to propagate the D to the output of the slave latch. And that was not the most efficient implementation of a D flip-flop, by the way. You could actually implement a D flip-flop in a much nicer way, let's say, but it was easier for us to actually show that with logical signals at that time. So basically, you need to obey these setup and hold time constraints. So setup time is the time before the clock edge that data, or D, must be stable. Stable meaning not changing. It should stop changing at that point. Before that, it could change. But at this point, until the clock edge, T setup time, it should not change. And hold time is time after the clock edge that the data must be stable, because the internal circuitry of the flip-flop may actually be processing that data before or after, essentially. Okay, essentially, aperture time is the time around the clock edge that the data must be stable, and aperture time is T setup plus T hold. So this is very fundamental. This is how a flip-flop operates, and we're going to base every discussion of a sequential system based on this assumption. So usually, let me put it this way, currently people try to minimize the hold time as much as possible to 0, but that's not always the case. People play a lot of tricks internally to minimize the hold time, but that's not always the case. So you still need to worry about that if your flip-flops don't have 0 hold time. And usually they have non-zero, almost always actually, they have non-zero setup time. Okay, so before we go into this, let's talk very briefly about metastability. Basically, if D is changing while it's sampled, metastability can occur. And this was also something we discussed when we talked about the SR latch, right? Essentially, the flip-flop output becomes stuck somewhere between 1 and 0, and output eventually over time settles non-deterministically. You don't actually know what it will settle to. It may settle based on the variation in some components of the circuit, for example. And this is one example of metastability, for example. So this is, if you have a NAND, this is from NAND RS latch, and this is real simulation. And you can see that the clock changes and Q changes, because the data is not shown over here, but fine. But after the clock changes, Q changes, but it settles to some value between 0 and 1. So assume that this is 1, assume that this is 0. And you can see that it settles to some value between 0 and 1 for some time. It's metastable. And then there are many possible paths it can take. So these are simulations of many different potential paths the Q value can take. So it may go to 1, it may go to 0, but you don't know basically what it will go to. So this is why you should really avoid changing D in this aperture time window. Because if you change D in the aperture time window, the circuit is not guaranteed to be stable. It becomes metastable. And the output you get may be D may get Q may get D, or Q may get not D after it's, of course, stabilizes. And it may take some time to stabilize, which actually causes some delay in your circuitry. So it may mess up everything downstream in your circuitry. So essentially, don't violate the aperture time requirements. Okay, so let's talk about the output timing over here in flip-flop also. So that was the flip-flop D to Q timing. Now this is the output timing, clock to Q timing. So flip-flop, as you can see, that's 2 inputs, right? One is D to Q, and there's some timing requirement from D to Q, as we discussed, the setup time and the hold time. There's also a timing requirement from clock to Q, as you can see. After clock rises, Q starts changing, and that's the clock to Q contamination delay. That's the minimum time it takes after clock changes or rises for Q to change. And this is really very similar to the contamination delay of a gate, as we discussed earlier. This is the minimum possible delay of the flip-flop from the clock. And PCQ is the maximum possible delay for Q to change after clock changes. Essentially, this is a delay after which Q definitely settles. And that's the propagation delay from C to Q. Okay, and that's the definition basically. Contamination delay, clock to Q, TCCQ, is the earliest time after the clock edge that Q starts to change. In other words, it's potentially unstable, but it may also change. That's the shortest possible path, let's say, from clock to Q. And propagation delay, clock to Q, is the latest time after the clock edge that Q stops changing. meaning that it becomes completely stable. And this is the longest possible delay from clock to Q. And this is going to be important because this is going to affect how long it takes for us to get the Q. Clearly, Q is going to be used, which is the flip-flop output, right? It's going to be used in some combinational logic inside a finite state machine, right? Or as part of your sequential system. So this delay affects when Q is available to you, right? And that delay, it needs to be added to your combinational delay to really get how long it takes for you to get the result out of a computational circuit starting from the clock rising edge. That's why this delay is extremely important. Again, that's true for the shortest signal as well, right? You need to know both the shortest path and the longest path, so that's why we need to know the shortest clock to Q and longest clock to Q delays. Okay, now let's talk about sequential system design. Essentially, a sequential system looks like this. And this is very similar to a finite state machine, except we're not going to put the output of the combination logic or next state logic from here to here, but we're going to latch the next state, latch the output of the combination logic into some other register. And we're going to see why this is beneficial later on when we talk about pipelining, for example. You have some system, there are some inputs which are in this register, let's say, or it could be it's based on flip-flops. And then you operate on those values. You do something combinational that results in some output, and then you latch the data in some other register. And this takes some clock cycle time. And this is really the clock cycle time of your processor, for example. And we will see later on how this is determined in pipelining. Don't worry about that right now. But assume that we have a system that operates based on this. You have R1, and then combination logic. Result is latched to R2. And then you take the output of, the value in this over here, put it into another combination logic, and then the result is latched to R3. And then you take the output of R3, put it into another combination logic, the result is latched to R4, ... That way you can actually do many combinational operations in the same clock cycle, and then move the data in a pipeline manner to the next stage, if you will. Don't worry about it if you don't understand it that way, but that's the reason why we're plotting it this way over here. The same thing applies actually absolutely the same way if you actually take D2 and put it into this register, except it's going to, you can also think of it that way, basically. So you can think of it as a finite state machine where you take D2 and put it back into this register, state register, or you can have it as a sequential system where you have multiple different state registers and combinational logic sits in between multiple different state registers. It's the same thing in the end. And the timing analysis will be very similar because they're both registers, and we're going to assume that those registers are the same. Okay, so basically you have multiple flip-flops connected with combinational logic. We call them registers here, but essentially a register is made out of multiple flip-flops based on the bit width. And clock runs with a period. We're going to call this the cycle time. Now, this period is going to be given to us, or you determine it based on the maximum combinational logic delay. Usually what happens is it's determined based on some requirements, like for when you want to compete in the market. You say, my clock period is going to be 5 gigahertz, and you try to achieve it. You can actually achieve it by minimizing the combinational logic that you have, while adjusting the combinational logic that you have between these sequential flip-flops, right? So basically, we have some control over the clock cycle time. But we're going to assume that clock runs with period clock cycle time, and we're going to try to compute it. And minimizing it, we'll discuss in a little bit also. Basically, to be able to do this design, you need to meet this timing requirements for both R1 and R2. And again, if R1 and R2 are the same thing applies. You still need to meet the timing requirements for R1 and R1, essentially, because you're going to take the data value over here and put it back into R1, right? So that's the key over here. If you want to really design a sequential system that looks like this, which is all computing systems that we have, you need to meet the timing requirements. So we're going to analyze the timing requirements. So how do we ensure correct sequential operation? So basically, you need to ensure correct input timing on R2 over here. And this is why things will become easier if you think about things as R2, for example. So basically, you need to latch the output of the combination logic D2 into R2, and you want to latch the correct data, right? You don't want to latch a glitch, and you certainly don't want to latch something that is computed before the worst case delays. That's why you need to take into account the worst case delay from clock to all the way into Q over here, as well as any possible thing that can affect the worst case delay from any input over here to the final latching of the data in R2. Okay, specifically, as we discussed earlier, the D2, which is the input signal to register 2 over here, must be stable during the aperture time of this flip-flop register 2, meaning that D2 must be completely stable, at least T setup time before the clock edge, and at least T hold time after the clock edge, right? As we discussed, right? It's the same thing, basically. You need to obey these requirements, but we're going to work our way backwards over here. So that means that you need to have enough time here after D2 is stable to set up and also hold. Okay, now let's take a look at how this really affects the computation of the delay over here. We're going to compute the delay. This means that there is both a minimum and maximum delay between the two flip-flops. Again, if you want to imagine as a single flip-flop where the combinational output goes to the flip-flop, it's the same thing, basically. Okay, so this is what we're going to look at. So we have a clock cycle time. Assume that it's determined in some way, and that's really the time between two rising edges of the clock, two consecutive rising edges of the clock, and that's obvious, hopefully. And during that time, you are going to compute in the computational logic, right? At this point, the data value is going to be latched. After some point, Q1 will be completely available to the combinational logic, as you can see over here, which is this part, clock to Q1 propagation delay. And after some point, computational logic will settle. That's the Q1 to D2 propagation delays, which is really the propagation delay of this combinational logic. And then you need to have enough setup time over here. But then there needs to be some hold time over here, as we will see also. Okay, so basically, let's take a look at the hold time over here first. So if, for example, the combinational logic is too fast, so let's assume that, let's go back to this picture over here to make sure we understand the hold time. So what does the hold time say? The hold time of this register 2 says that D2 should not change too fast, meaning that after the clock rises, you can see that the clock is rising over here. And assume that the clock is rising at the same time for both registers over here. After the clock rises, this D2 must be stable for a while. Now, this may be violated if this combination logic is too fast, right? What does that mean? That means that if this combination logic quickly changes from 0 to 1 within the T hold time, after the clock changes over here, then you may actually violate the hold time of the second register over here. That's the idea, basically. That's what I mean by combination logic being too fast. So if this combination logic is too fast, it may evaluate so fast that this register 2 doesn't have time to sample it within its hold time. As a result, you may actually violate the hold time of this register 2. Okay? And we don't want that, clearly, because we will sample something wrong then. Okay, you can see that, right? So a clock to D2 over here should be less than the T hold time of this register, so that we can avoid a potential R2 T hold violation at this register. Okay, so hopefully that's clear. Okay, if the combination logic is too slow, meaning that if D2 becomes available too late in the clock cycle, or maybe it doesn't even become available in the clock cycle, right? It's too long. This combination logic takes too long to evaluate. You may actually violate the setup time of this register 2. Because what does the setup time of this register 2 say? Let's go back to this picture over here. It basically says, before the clock rises, we need to have some time for D to be completely stable. Otherwise, we may sample something wrong, or we can become metastable, as we discussed, right? So basically, we want to ensure that clock to D2 over here doesn't violate the T setup, right? And we're going to write up equations to ensure that, basically. And we want to ensure that we don't violate that T setup. Okay, so let's take a look at the setup time constraint first. So I'm going to write equations right now. So safe timing depends on the maximum delay from R1 to R2, as I've shown you in this picture. Actually, this is maximum delay, if you will. And the input to R2 must be stable, at least T setup before the clock edge over here. So let's take a look over here. So we have T setup, and the D must be stable for at least T setup time. as we discussed over here. So we have a T clock cycle. Assume that it's given to us somehow, but we're going to make sure that it's greater than some value, so that so basically, don't assume that it's given to us. Basically, we're going to compute the minimum possible clock cycle time that is required by this combination logic and the sequential system. So first of all, you need to ensure that you're greater than the T setup. Okay, let's start from the beginning. Actually, first of all, you need to ensure that the input R2 must be stable at least T setup before the clock edge. But then there are other delays, right? Certainly, the input of this combination logic becomes available from the earlier register in TPCQ amount of time. Remember, what this was is clock to Q delay, propagation delay, which is the worst case delay from clock to Q. So that's the worst case delay over here. And then in the combination logic, we have some propagation delay. Assume that it's fixed for now. So that takes some time. And then we need to ensure that we wait enough time, the setup delay, for D2 to be available in the clock cycle. And this is what our clock cycle equation is. T clock cycle should be larger than clock to Q propagation delay, and then the propagation delay of the combination logic, and then the setup delay of this register. Okay. Okay. So basically, as you can see, the useful work over here is really the combination logic, right? Assuming that you optimize it, of course, right? You may waste a lot of delay over there also if you didn't optimize it. But this is assume that this is useful work. The PCQ and setup times are completely wasted work, and we call the sequencing overhead. This is really the amount of time wasted each cycle due to sequencing element timing requirements. So whenever you have synchronous circuits that are clock-based, you have the sequencing overhead, basically. And we have to pay the sequencing overhead. And if your clock cycle is actually very small, then actually this overhead may be very, very large as a fraction of the clock cycle. So I think one of you may be asked, what if the propagation delay of the combination logic is too large? Then you increase your clock cycle. But what if somebody says your clock cycle should be 10 gigahertz or 5 gigahertz? Then you actually make sure that you don't put too much combination logic to increase your propagation delay. So basically, you can control your clock cycle time by changing your propagation delays, by changing what you put into the combination logic clearly, right? And by separating it into multiple stages, right? For example, if you need to complete an addition, you can say, oh, I'm not going to do the addition in 1 clock cycle. I'm going to do it in 2 clock cycles because I want to increase my frequency, and I want to do part of the addition in this clock cycle and part of the addition in the next combination logic over here. That way, you can reduce the clock frequency. You can reduce the clock cycle time of the addition while essentially having a good frequency, while satisfying the frequency requirements, right? So that's the idea, basically, and that's how we can pipeline the circuits as we discussed. So what I just told you is a form of pipelining. You don't do the full addition in 1 cycle. You just do half of it over here, and then latch the data value, and then half of it in the next clock cycle, if you will. Okay, if you didn't understand it, don't worry about it. We'll talk about pipelining. But you have some control over your TPD, actually, depending on how you design your sequential system. Okay, so this was the sequencing overhead. Now let's take a look at the T setup constraint and the design performance. So remember, critical path is the path with the longest TPD, right? Now, overall design performance is really determined by critical path TPD, and then you pay the sequencing overhead on top of that, right? So a TPD determines the minimum clock period, max operating frequency, but that's not enough. You also need to add TPCQ and T setup times. If the critical path is too long, the design will run slowly, clearly. If the critical path is too short, each cycle will do very little useful work, meaning that most of the cycle will be wasted in the sequencing overhead, TPCQ plus T setup, as we discussed. Now, let me cover the hold time constraints. We covered the setup time constraint, which really affects your critical clock cycle time, as we discussed. Let's cover the hold time constraint, because that's going to make things a little bit interesting. So safe timing also depends on the minimum delay from R1 to R2. And now hopefully it'll become clear why minimum delay matters. I promise that I will talk about minimum delay and why it matters. It matters because of the hold time constraint, basically. So let's take a look. Essentially, D2, R2 input must be stable for at least T hold after the clock edge. If the combination logic is way too fast, this may not be maintained, right? So basically, D2 must not change until T hold after the clock. So what does this mean? So what is the minimum delay from clock to D2? It's really the minimum delay from clock to Q for the combination logic to start as with Q1 as the input. That's the minimum delay. That's CCQ, as we discussed, plus the minimum delay, contamination delay, from the combination logic, within the combination logic. And we already discussed that. That's the shortest path. Basically, that's the shortest delay from clock to Q and the shortest delay from within the combination logic. If you add them up, they have to be greater than the t-hold. That's what the hold time constraint means, right? Because if they're smaller than t-hold, then you're violating the t-hold constraint and the aperture time, and you may be sampling a wrong and changing value, and you can become metastable in R2, right? Okay, so if you actually rewrite this equation, this means that TCD should be greater than t-hold minus TTCQ, which means that you need to have a minimum combinational delay, right? Unless this is negative, of course, right? Unless TCCQ is already large enough, or t-hold is already 0, right? So in many cases, t-hold may be 0, or t-hold may be smaller than TCCQ. As a result, this may not matter. But in some cases, this may not hold. As a result, you may need to do something about it. And what is that something? Well, something is adding additional delay on the minimum delay path, right? Shortest path. Adding buffers, for example, right? That's the idea. So hold time constraint is actually a bit dangerous. It doesn't depend on the clock cycle time, as you can see. It completely depends on the minimum delay path and the hold time and the CCQ time, as we discussed. And it's very hard to fix t-hold violations after manufacturing. You must modify circuits, basically. Or you need to have reconfigurable circuits in some way, right? Because you can easily fix setup time violations or clock cycle violations after manufacturing, right? Run your clock slower, slow enough that you don't have these violations. But hold time violations, sorry, you cannot fix them by changing the clock because it's independent of the clock frequency or clock cycle time. Okay, so let me summarize this, and then we're going to take a break. So hopefully this is really interesting. I find all of this fascinating. But imagine you're doing this for a very complicated circuit. We're doing it with essentially right now abstracted circuits, right? If you do it with a complicated circuit, this becomes even more complicated. So this is the summary of what we have seen. TCCQ and TPD are combination logic delays minimum and maximum. T setup is the time flip-flop inputs must be stable before the next clock edge or before a clock edge. And T hold is the time that flip-flop inputs must be stable after a clock edge. And TC is a clock period, as we discussed, right? So you can actually, you need to obey all of these equations that I showed you earlier. Let me do some timing analysis now. And this is from your book also. And this is one circuitry, as you can see. It has 4 inputs, 4 flip-flops, A, B, C, D, and then 2 outputs, X, Y. They're both controlled by the clock. And you can see that the combination logic is relatively simple over here. And these are the values that we are given. CCQ, PCQ, T setup, T hold, and the per gate propagation and combination logic delays. They're given per gate, and all gates are essentially assumed to be same in this case. So let's take a look at both the setup time. So for this circuit to work, you need to make sure that the setup time constraints are obeyed and the hold time constraints are obeyed. And these are the equations that I showed you earlier. T clock cycle time must be greater than the summation of PCQ, PD, and setup, and TCCQ plus TCD must be greater than the hold time. And I've given you all the reasons for it. Now let's calculate the PD and CD over here. We already given the TPCQ, right? It's 50 picoseconds over here. And we already given the setup over here and CCQ over here and then hold over here as well. So what is the PD? So PD is essentially 3 times 35 picoseconds, 3 gate delays, 105 picoseconds. CD, which is the contamination shortest path delay, is really 25 picoseconds. It happens in 2 possible cases, right? Okay. So now we plug in the numbers to the equations. So our clock cycle time should be greater than TPCQ, clock to Q delay, maximum, plus maximum propagation delay through the combination logic, plus the setup time, which is 215 picoseconds. So basically, assuming that you leave your combination logic as is, your maximum clock frequency can be 4.65 gigahertz, which is 1 divided by the clock frequency, clock cycle time, right? In this case, which is not bad, but we're only using 3 logic gates here. So you really want faster logic gates if you really want to maximize your frequency, as you can imagine, right? Okay, so here there's nothing to really change, if you will. The only thing that you can change is TPD. If you say, okay, I'm not reaching 5 gigahertz, so let me try to change TPD. And there are multiple ways of changing TPD, which is getting rid of one gate and doing it later in some other cycle, later in some other combinational logic, or getting faster gates, as I said. Or you increase your clock frequency and basically say, okay, I wanted 5 gigahertz, but I'm not achieving 5 gigahertz. I'm not willing to do more design changes. I'm going to stick with 4.65 gigahertz. Okay, so this is easier to handle in a sense. But of course, if you're targeting a very aggressive frequency, it may be, you need to be aggressive in how to handle it. Okay, hold time is not as easy to handle as we discussed. Let's take a look first. Is there a problem? TCCQ, okay, TCCQ plus TCD must be greater than our hold time. And in this case, TCCQ plus TCD is 55, and it's not greater than 70 picoseconds. So this circuit will fail, which means that you need to go back and do something about the hold time constraints. So how do we fix the hold time constraint? As I mentioned, you need to add buffers basically, and enough buffers so that the hold time constraint doesn't get violated. So the short paths are essentially, if the hold time constraint is being violated, that means that the short paths are too short. So you need to make them long enough to not violate the hold time constraints. Okay, so let's take a look now. Assuming that we add buffers to the short paths like this, now you can calculate the propagation delay, maximum delay, didn't change, but the contamination delay actually changed to 50 picoseconds. So our clock frequency didn't change because we didn't change the maximum delay. We did change the, so max frequency didn't change, that's good. But now we passed the hold time violation, right? Because we added a buffer that takes about 30 picoseconds. Well, it's somewhere over here. Sorry, it takes essentially 25 picoseconds. Sorry, because each gate contamination delay is 25 picoseconds, and then now you have 2 gates in the shortest path, so you basically pass. So this was not desirable, as you can see, right? We didn't really want this, but we had to do this because of the hold time constraints of the flip-flop, and that's a fact of life. This is exactly why a lot of flip-flops are very, very carefully designed to really minimize the hold time constraints, essentially. But you may actually get hold time constraints, and if you violate them, your life will be very, very complicated. Okay, so I think this is a good place to take a break. We're going to take talk about clock skew, which is also going to be very important. But I think this is going to be a good time, because clock skew is something that's going to add a little bit more time into the clock cycle time. So let's take a break until I guess 3:35. I'll give you a 10-minute break, and then we're going to cover the rest. And then we're going to talk about clock skew. So remember, this is where we are. Basically, we looked at sequential system timing, and you need to make sure you obey the setup and hold time constraints in a sequential system to make sure that everything works. And these constraints are really determined by the sequential element timing, which is a flip-flop timing. And those are based on when you actually sample the data while the clock is rising, right? So that's why this is really important. But clock skew actually affects both of these timings, as we will see. And what does this mean? Basically, so far we've assumed that clock doesn't have any delay. It arrives, so if you go back to the system that we're examining, actually this is fine. If you look at the system, clock arrives at the this first set of flip-flops, let's say R1. At the same time, it arrives at the second set of flip-flops. But that's not necessarily true also. There's a delay in the clock distribution in real systems. And the clock doesn't reach all parts of the chip at the same time. It may reach R1 a little bit earlier or later, depending on how it's distributed. And clock skew is the time difference between 2 clock edges that are input to different registers. So you can see the clock source, and then it goes to register A and register B, and there might be a delay associated between the time it changes, the clock changes at A versus B, because of the way it's distributed, right? And that leads to a timing diagram that looks like this. So clock doesn't immediately appear at all of the registers at the same time, but there's a skew at which it appears in different registers, in different points, let's say. And this is one real example from a real chip. This is Alpha 21264, which was designed in the mid to late 1990s. And this was the fastest processor of its time, actually. And you can see there's a distribution of the skew of the clock in terms of the physical location where it goes in the chip, right? And you can see this spatial distribution of the skew. And you can see that at some places the skew is very small, closer to 0, let's say. But at some places the skew is closer to 70 or 60 picoseconds. So there's a huge difference in the delay. And you can see that this looks like a mountain shape. There are 4 mountains over here. This is because the clock is distributed in terms of a tree structure in this chip. You have essentially a tree, as we will see in a later slide. And that tree determines the shape of the skew also. And also there's manufacturing variation, etc., that affects the skew that you see. And that affects these edges, for example, that you see over here. Okay, so let's take a look at the setup time and revisit it when we consider the clock skew. So safe timing now requires considering the worst case clock skew. So let's take a look at this. So let's assume that the clock arrives at R2 before it arrives at R1, which means that it leaves as little time as possible for the combinational logic, right? Because what happens is if it arrives at R2 before it arrives at R1, now there's some clock skew that needs to be added because the time that's available for the signal Q1 over here is much smaller than before. If it arrived at the same time, then you would have more time. But because it arrives earlier over here and later over here, you have less time within this combinational block, right? So this is the picture of it over here. Basically, clock 1 comes late. That's the darker shaded clock over here. And clock 2 comes early. Now your delay is clock to Q1 propagation delay plus the propagation delay of the combination logic plus the setup time plus the skew, right? Because there is some skew that you need to deal with over here, right? Okay, so essentially signal must arrive at D2 earlier, and this effectively increases your T setup time, right? So now basically the equation for your clock cycle time is time from clock to Q propagation delay plus the propagation delay of the circuitry plus the setup time of the second latch plus the clock skew. You need to take clock skew into account now because we ignored it previously, which essentially increases your setup time now. Basically, your setup time, effective setup time, is not just the setup time, but the skew at which the clock arrives. Because the clock arrives early over here, you're really, you can also think of it as clock is arriving early at register 2, which means that your aperture time or setup time is really increasing at R2. Okay. Now, if the clock arrived before earlier at R1 before R2, this would not be a problem, right? Now you have more time in the combination logic, so setup time would not be a problem, but your hold time may be a problem in that case, right? Because now this you're much faster over here and you're slower over here in terms of when the clock is. Okay, so basically you need to take this into account. Now let's take a look at the hold time now. And this is basically what I'm going to say, what I just said earlier. If the clock arrives earlier over here, then hold time will become problematic, right? So basically, safe timing requires considering the worst case skew again. Clock arrives at R2 after R1. That's the worst case over here. So if it arrives at R2 after it arrives at R1, then you have more time over here in this combination logic. And essentially, you need to make sure that your combination logic still obeys the hold time requirements of the R2. And this increases the minimum time required for the combination logic, essentially. So let's take a look at this over here. So clock 1 arrives early, which for R1, clock 2 arrives late over here. So you can see the clock to Q minimum delay, contamination delay, puts us over here. And then we have a contamination delay over the circuit. So now TCCD plus TCD should be greater than T skew plus T hold, right? Because T skew is over here, as you can see, right? There's a skew amount of time that is essentially eaten up by the clock delay. Okay, basically signal must arrive at D2 later, and this effectively increases T hold, as I said over here. TCD plus TCCQ must be greater than T hold time of the register plus the clock skew. And we call this T hold effective. Essentially, because of the clock skew, effective hold time of the register increases because you have additional delay for your signal to be stable after the clock arrives there because of the skew, right? Okay, so hopefully this is clear. I mean, this is intuitive if you think about it a little bit, but a lot of things that we discuss over here require some thinking to settle. You may not immediately understand everything that I explain. If you do immediately understand, that's great, actually. But usually this requires some thinking, and usually that thinking is actually needs to be done a little bit offline, in my opinion. And if you really want to understand these, I would recommend going through the slides plus going through the chapters that I mentioned earlier in Harris and Harris. This topic doesn't appear in Pat and Patel, but in Harris and Harris this appears, and it has a very good explanation of these concepts. Okay, to summarize, skew effectively increases both T setup and T hold, essentially. Things that are a part of our sequencing overhead, right? Essentially, it increases sequencing overhead, meaning that it causes less useful work done per cycle. So designers in general must keep clock skew to a minimum. And this requires some intelligent clock network across a chip. And there's a lot of research on this topic at the lower level, clock distribution. Actually, this is true for power as well. How do you distribute power? But I'm not going to even go into the power at this point. So essentially, the goal is to ensure that clock arrives at all locations at roughly the same time. But it's easier said than done. So you can see that there are many, many different types of clock networks, if you will, that are designed to distribute the clock. So you have a source for the clock, and then you basically distribute it across your entire chip, let's say. The question is, how do you distribute the clock from the source, let's say the ring oscillator, all the way to every single circuit that needs it in a way that minimizes the skew? And there's a lot of work in this topic that I'm not going to go into. But in the end, you cannot get rid of the skew. You can reduce it, but you cannot get rid of it. Okay, so let's talk about circuit verification in the next parts. These next parts are going to be interesting and easier and more practical from your lab perspective, because in your labs, you'll have to deal with verifying your circuits. And the key question in circuit verification is, how do you know that a circuit works? You have designed a circuit. Is it functionally correct? That's the first question. Even if it's functional correctness is the same as logical correctness, basically. Even if it's functionally or logically correct, does the hardware meet all of the timing constraints? Now, the question is, of course, how do we do this verification? How can we test for functionality and timing? And the main answer that we're going to use in this course is really simulation tools. So Vivado, for example, in this course is going to be your friend to enable functional verification, timing verification. You could also do a circuit level simulation at the lower level, like SPICE is another tool for circuit level simulation you're not going to deal with over here. If you take a microelectronics design class, for example, you will deal with SPICE. Or you could formally verify a circuit. This is especially true for functionality. Timing is much harder, but you could use, for example, satisfiability testing solvers, SAT solvers, in other words, or formal verification tools, other similar formal verification tools, to formally verify that your circuit actually does what is intended to do. And we're not going to talk about that. Also, again, if you take a formal verification class, they may cover hardware design, because some of these formal verification tools are applied to hardware also. But in this class, we're going to talk about simulation tools quite a bit. So this brings us to testing large digital designs. So testing, as I said at the beginning of this lecture, can be the most time-consuming design stage. You need to ensure functional correctness of all logic paths. You need to ensure timing, power, etc., of all circuit elements. They're within the bounds and they're correct. Unfortunately, low-level simulation is much slower than high-level simulation. So circuit-level simulation, SPICE simulation is much slower than Vivado or C-level simulation. So basically, we normally split responsibilities in this. We usually check functionality only at a high level, like C or hardware description language, because this allows us to simulate fast with high code coverage. And we can easily write and run tests at that high level of abstraction because things are much faster. Whereas if you do it at a circuit level, things are much slower. And also, you need to be more detailed in the modeling, which makes the modeling slower also to begin with. And also, we check only timing, power, etc., at a lower level or circuit level. And we usually don't do functional testing, whether the circuit implements this function using a low-level model. But we test the functional equivalence to the high-level model. So if we have a circuit model, is it really equivalent to the higher-level model? Now, this is hard, but easier than testing logical functionality at that level. Again, I'm not going to go through the details of this. Your book actually has more detail, and some other books have even more detail. So we have tools to handle different levels of verification. Logic synthesis tools guarantee equivalence of high-level logic and synthesized circuit-level description. So basically, you write in hardware description language, you give it to a tool that synthesizes the hardware description language, and hopefully somebody verified it formally or with some other testing methods that it's guaranteed to be correct. That's what you're relying on over there. Timing verification tools check circuit timings, and sometimes your synthesis tools actually do that also. In fact, you will see that they will, but they may not be perfect in this case. And then there's design rule checks that ensure that physical circuits are buildable. This is basically whether the transistors are too close to each other, for example, whether the gates are too close to each other, whether you make sure that the wires are large enough to carry the load that they're subjected to. Clearly, we're not at that level in this course. This is at a lower level than what we're going to cover in this course. So we're not going to talk about design rule checks. But the task of a logic designer is to provide functional tests for logical correctness of the design and to provide timing constraints, or for example, the desired operating frequency, to make sure that the design actually works, right? And also you need to somehow make sure that the hold time constraints are not violated, right? That's also the task of a logic designer, unfortunately, as we have seen earlier. So basically tools and or circuit engineers will decide whether the design can be built in the end. So if you're synthesizing your design, tools will make sure that whether the design will be built or not, or give you an answer, let's say. And if you actually are designing the circuit via circuit engineers, or you're designing it yourself, you will decide if it can be built. Okay, so that's part of the verification. Let's talk about functional verification, because you're going to do a lot of that basically in the course. You're actually hopefully doing that already. Basically, the goal is to check functional or logical correctness of this design. Well, you can also think about it as Boolean functionality, right? Does this circuit implement the Boolean function that it is supposed to implement? So in this verification, usually we ignore physical circuit timing like T setup, T hold, because you don't want to mix things at the conceptual level, and this becomes just a nuisance at that level. You may implement simple checks to catch obvious bugs if you want to, but we'll discuss timing verification later in this lecture as part 5. There are two primary approaches to functional verification. One is logic simulation using test routines, for example, C, C++, Verilog, or you can use formal verification, as I said, using SAT solvers. We're not going to do SAT solving or formal verification, but we're going to do logic simulation in this course. And we're going to use Verilog for functional verification, and we're going to build test benches in Verilog to be able to do that. So let me introduce test bench-based functional testing. Test bench is essentially a module that's created specifically to test a design. Tested design is also called DUT, or device under test. And the test bench looks like this at a high level. Basically, you have a test pattern generator, and there are multiple ways of generating test patterns, which are applied to inputs. And then you observe the outputs at the end, and you check whether the outputs actually correspond to the correct outputs that you determine somehow, as we will see. So test bench provides inputs or test patterns to the design under test. And design under test could be either the entire system, or it could be part of a system. It could be, for example, the sequential system that we showed earlier. The question is, how do you provide the test patterns to test the system? You can have test handcrafted values, or you can have automatically generated values, sequentially generated. You basically start with, let's assume that you have 3 inputs. You enumerate all possible inputs, for example, right? Let's say you have 32 inputs, maybe you randomly test different inputs. That may or may not be a good idea. And the test bench checks outputs of the design under test against handcrafted values, golden outputs that you know to be correct, or compares it to the output of a golden design that's known to be absolutely correct or bug-free. We will see these differences between these two approaches in a little bit. So basically, a test bench can be a hardware description level, language level code written to test other HDL modules, or it could be a circuit schematic used to test other circuit designs. Test bench is not designed for hardware synthesis. This is not something you synthesize. I mentioned this in the last lecture, but hopefully it's clear. The goal is really to run it in simulation only to check whether the functionality of your circuit is correct. And you can do it in HDL simulation. You can do it in SPICE simulation. Essentially, you can do it at any level of simulation that you are comfortable with, if you would like. Testbench uses simulation-only constructs also. For example, you can say, wait 10 nanoseconds. We discussed this in the last lecture very briefly. You can apply these inputs at any time you want to see the waveform and when it changes, for example, so that you can actually test whether your system is functionally correct under different delays, for example. And then we assume ideal voltage current source, of course, and this is not suitable to be physically built. So let's take a look at common Verilog test bench types. Essentially, there are multiple. So there could be a simple test bench where everything is done manually. Input, output generation, and error checking, results checking, let's say, are done manually. So there's a lot of work for the designer, but for small circuits, it might work. Self-checking test bench, input, output generation is manual, but error checking is automatic. So you automatically compare things. And automatic test bench is basically both input, output generation, and error checking are automatic. So let's take a look at some of these. So we will walk through different types of test benches you may design during your labs, for example, to test a module that implements a simple logic function. As you can see, it's very simple, right? And at the end, this is another silly function, another one of those silly functions. And this is its Verilog implementation. It's not the greatest implementation, as you can see, but it's the most explicit implementation over here, as you can see. So we basically explicitly instantiate inverters as well as gates, the min-term gates that do the ANDs, and then we have the OR gate over here. So this is a very structural Verilog, as you can see. So we are going to use Verilog syntax for test benching. Essentially, we have an initial block. It's like the always block, but runs only once at simulation start. So these are actually for simulation. These are Verilog constructs for simulation purposes. So we can set the value of a register to 0 this way, and then use a blocking assignment, and then wait for 10 nanoseconds, do nothing, and then A becomes 1. So this way you can simulate basically. And you can keep adding these things manually to your Verilog code, as you can see, so that you can decide when the inputs change. And then you can also display print messages, very similar to print-based debugging, right? So let's take a look at our simple test bench. So we instantiate our silly function, dot, and you saw the Verilog implementation of it earlier. And this is the test bench module, as you can see. And we have some registers and wires that are manually assigned. So this is going to be our manual test bench soon. And basically, we have an initial begin section, and then we apply hard-code inputs one at a time. Initially, we apply A, B, C, all zeros, and then wait for 10 nanoseconds. And then we change C to 1, wait for 10 nanoseconds. And then we change B to 1 and C to 0 to wait for 10 nanoseconds. And you keep doing this basically. And at the waveform, you observe what the result is. Result is Y over here. And while you simulate the circuit, the silly function, by applying inputs consecutively at different times, now you can see in the waveform output changing, and you basically verify whether the output corresponds to the correct output given an input. Right? It's so simple, basically, from that perspective. So basically, most common method for output checking is looking at waveform diagrams, as I mentioned. Basically, you apply some inputs, and you get some output, and you check the output at the right times. Now, of course, there are thousands of signals over millions of clock cycles. Printf is not a great way of debugging. Waveform also may not be a great way of debugging if actually you have many, many outputs, for example, if you need to check a lot of things. So manually checking that output is correct at all times is good. And it's good when you're learning, when you look at small circuits, but it doesn't work very well with very large circuits also. So pros, essentially, with the simple test bench, completely manual, is easy to design. You can easily test a few specific inputs, for example, corner cases, but it's really not scalable to many test cases on large circuits also. And outputs must be checked manually outside of the simulation somehow. You can inspect dumped waveform signals, you can do printf style debugging, but none of them are really that scalable. So that brings us to the self-checking test bench, which is a little bit more advanced, let's say. Basically here, the key distinction is you apply the input, you apply the input, wait for some time, and then you check whether the output is correct. And then if the output is not correct, now you're encoding the outputs inside the test bench itself, as you can see. So the output is not 1. You display, okay, this input failed. And then you apply another input. If the output is not as expected, you display it's failed. And you can do it in different ways, of course. You can do it via post-processing, etc. I'm not going to go through details. But again, this is still easy to design, still easy to test a few specific inputs like corner cases. And simulator will print whenever an error occurs if you do it nicely. So output checking is automatic, if you will, over here. But still, it's not very scalable to millions of test cases. And again, easy to make an error in the hard-coded values that you see over here. Basically, you make just as many errors writing a test bench as actual code over here. So it's not clear if this sort of test bench is really that scalable to very large circuits. And I don't think it is actually. And it's hard to debug whether there's when you have an issue, when you have an output failing, for example, whether there's an issue with your original circuit or whether it's an issue with your test bench. So now your test bench may introduce errors also. This doesn't sound good, right? So we need to be careful. So the next way of doing self-checking test bench is using test vectors. So now you can write a test vector file. You can be more intelligent. You can say, okay, I want a file, list of inputs and expected outputs. Now you can create vectors manually and automatically using an already verified simpler golden model. We'll see this later on. So this is one example test vector file, for example. If for input, 3 inputs, 0, 0, 0, output should be 1. 0, 0, 1, output should be 0. And you keep doing this for 8 inputs. So that's the format. So with small circuits, it's easy to write. With large circuits, it's also a bit easier to hard code in the Verilog again, right? Because now you're doing it in a methodical way in a file. And now you use a clock signal for assigning the inputs and reading outputs. Now you can actually automate this much better, right? Let's take a look at how this is done. So basically, you test one test vector each clock cycle. Don't confuse this clock cycle with the timing that we discussed earlier. This is just for testing. It has nothing to do with the clock cycle of the circuit itself. Basically, this is the clock cycle that we use for testing. At the rising edge of the clock, we apply the input. At the falling edge of the clock, we check the outputs because we're doing functional simulation, right? And then at the rising edge of the clock, we apply the next test vector. And at the falling edge of the clock, we check whether the output of the circuit and see whether it matches the golden output. That's the idea. So basically, the goal of this clock signal is to simply separate inputs from outputs. It allows us to observe the inputs, outputs in waveform diagrams. It's not used for checking physical circuit timing. It has nothing to do with timing over here. The use of the clock is done just for the purpose of testing over here. And later, we will discuss circuit timing verification briefly in this lecture soon. But basically, this is an easier way of doing that testing. Essentially, we have this test bench 3. Now we have test vectors. You can see we can have 10,000 of these test vectors. And we have different vector numbers and errors, bookkeeping variables over here. We instantiate the device under test. You can see a more detailed example in H&H, as you can see. We generate a clock. And essentially, clock is high for 5 nanoseconds, and then it's low for 5 nanoseconds, and it basically keeps repeating, right? There's no sensitivity list, so it always executes. So forever, this clock keeps repeating, basically. And then this is what we do. The initial only executes once. You read the test vectors, and then basically do some reset, and then wait. And this is what you do for testing, basically. Always at the positive edge of clock, you apply ABC to take the first 3 values of the test vectors and y expected to be output, right? Okay, basically apply ABC inputs on the rising edge of the clock. That's what the circuit does. So hopefully it's simple. And then you get y expected for checking the output on the falling edge. And then rising and falling edges are chosen by convention over here. You can use any part of the clock signal if you wish. And the H&H textbook uses the rising edge to apply the inputs and falling edge to check the outputs, basically. Okay, this is your test bench, basically. This is the checking the outputs part, basically. If y is not equal to y expected, you get an error, basically. And then you basically keep, basically you get an error and you display the error. And then if test vectors, you reach the maximum, basically, you basically complete the test over here. So this is our test bench, basically. Over multiple slides, I showed you the test bench. This is the beginning of the test bench. This is how you generate the clock. This is how you read the file. This is how you apply each input in the test bench and get the output. And then this is how you check the output at the negative edge of the clock over here, as you can see. So this is clearly much more scalable, right, with test vectors. It's easy to design, easy to test a few specific inputs, but more than that, probably. Simulator will print whenever an error occurs, and no need to change hard-coded values for different tests. You basically deal with a test vector file in this case. So it's a bit more scalable, but it may be error-prone depending on the source of the test vectors. It really depends on how you generate the test vectors over here. If you actually generate them by hand, it's very error-prone. We will see how to generate them in a different way. It's more scalable, but still limited by reading a file. So you might have actually many more combinational paths to test than will fit in your memory. So this brings us to the automatic test bench, which is, in my opinion, the best way of testing. But this requires you to construct a golden model. So a golden model essentially represents the ideal circuit behavior, what the circuit is supposed to achieve. It must be developed independently and might be difficult to write. No question about that. It can be done in any language or even in Verilog, but you can do it in C, for example, whatever you're comfortable with at a high functional level. For example, for our example circuit earlier, this could be our golden Verilog model, right? Behavioral model. It's a high-level abstraction. Clearly, this is a silly function. So the golden model is simple, as you can see. But this is our golden model. It doesn't have a structural implementation. Basically, this is a functional implementation, which we hope is completely correct. Because it's simpler than our earlier gate level structural description, golden model is usually easier to design and understand, and they should be. Otherwise, your golden model is no better than your original design, right? And it must be easier to verify. So somebody needs to verify the golden model as well. Okay, so this is important. So think about golden models a little bit. Now, how you design an automatic test bench becomes interesting, right? So the design under test output is compared against the golden model. So basically, you have a circuit simulating the golden model. Sorry, you have a simulation simulating the golden model, as well as the design under test. And you apply the test patterns. It could be generated the way we discussed earlier to both the design under test and the golden model. And you basically compare the outputs. And if the outputs are equal, that's great. Design under test is golden. Of course, this requires that your golden model to be completely verified to be correct, right? The challenge is now there are two challenges actually. One is golden model needs to be correct, as we discussed. And also you still need to generate inputs to the designs. What do? Do you do sequential values to cover the entire input space? Do you do random values? How do you actually select your inputs to apply? And this is actually a fundamental problem. No question about that. Okay, let's take a look at the Testbench code over here. It becomes very simple. You have the silly function, inputs and output. You have the golden model. Inputs are the same as the silly function. Output is different. And you basically have a test pattern generation that applies the inputs to both circuits. And then if the output of the design under test is not equal to the output of the golden model, then you basically have an error at the negative edge of the clock, as you can see. Okay, so now it's fully automated, right? Output checking is fully automated. You can even compare timing using a golden timing model if you're aggressive enough. I'm not going to talk about that. It's highly scalable to as much simulation time as is feasible, at least a high coverage of the input space, but we're going to talk about input space in a little bit. Now you have better separation of roles. You can separate designers that work on the design under test and designers that work on the golden model, right? And the testing engineer can focus on the important test cases instead of output checking. Now you can actually really partition the work, and independent people can actually do independent designs plus the testing. Of course, the cons is creating a correct golden model may be difficult to very difficult. Sometimes maybe, I'm not going to say impossible, but not so easy to compare to the complexity of the original model. And coming up with good testing inputs can still be difficult. And that's true for all of the testing mechanisms, right? Regardless of the how automatic they are, testing inputs are a critical problem. Okay, now let's talk about testing inputs. Even with automatic testing, how long would it take to test a 32-bit adder? So a 32-bit adder has 64 inputs because you're adding A and B. Each of A and B has 32 bits. So you have 64 bits. That's 2 to the 64 possible inputs. If you test one input in 1 nanoseconds, you can test 10 to the 9 inputs per second. Or this many inputs per day, or this many inputs per year. Basically, you need 58.5 years to test all possibilities, which means that exhaustive testing or brute force testing of every single possible input is not feasible. That's why you need to be smart. You need to prune the overall testing space. You cannot do exhaustive testing, even for a 32-bit adder, as you can see. So you need to do some sort of pruning of the testing space, choosing important cases, eliminating as much as possible the cases that do not matter. Basically, there's a lot of work that is dedicated to designing test cases. Or you could do a combination of formal verification and testing, etc. I'm not going to go into the details, but this is one of the reasons why verification is a hard problem. In addition to everything we discussed, in the end, you're really limited by the length, the time to test. As a result, more than 70% of the design time of a cutting-edge microprocessor is spent on testing. That's true for memory also. More than 70% of the time of memory, like DRAM, for example, is designed on verification and testing. Okay, let me quickly cover timing verification. We're not going to go into much detail on this, and then we're going to conclude. Basically, there are multiple approaches to timing verification as well. You can do high-level simulation, like Verilog. You can model timing using the statements that we saw in the design under test, like the timing statements. It's useful for hierarchical modeling, clearly, to high-level simulation. You can insert delays in flip-flops, gates, memories, anything basically you want, including wires, actually, as we saw earlier. And high-level design will have some notion of timing in this case. But usually it's not as accurate as real circuit timing, because you may say, okay, this flip-flop is going to take 5 nanoseconds clock to queue, but it may not, right? It may take much longer or shorter. So the other approach that's more accurate is the circuit level timing verification. For this, you need to first synthesize your design to actual circuits, Basically, you have to go through high-level synthesis or whatever you do to actually create an actual circuit into your FPGA or ASIC, etc., or some low-level design netlist, let's say. And there's no one general approach over here. It's very design flow specific. Your FPGA or ASIC technology may have special tools for this. Usually they do. Like Vivado has some tools for this, assuming some backend that you compile into. But of course, real industry level tools, industrial grade tools are actually very much sophisticated, especially for VLSI design, for example. If you're really interested in this, you may take a VLSI design class. We have very good VLSI design class at ETH, for example. So there's a lot of interesting things that you can do over here, but it's very low level, as you can see also. The good news is tools that you use will usually try to beat the timing for you. If you say, okay, I want this clock frequency, these are my setup times, hold times, and this is the expected clock skew or whatever, it will try to meet the timing. But unfortunately, they may not always meet the time. They usually provide some sort of timing report, timing summary. They give you worst case delay paths as much as they can discover them, maximum operation frequency they expect, any timing errors that were found. They may be conservative in these. These tools are not exhaustively exploring the space, because exhaustively exploring space actually takes years, as we saw. So they may give you some idea of your timing. And you may go back and fix your timing based on these tools, but you always need to be careful about how much you rely on the tools. And the bad news is the tool can fail to find a solution sometimes, so you're back to square one. Desired clock frequency may be too aggressive. As a result, you may have a setup time violation of a particular long path. The tool may be able to report that potentially. That's good. But still, it may not be able to find it. So you may actually need to go back and modify the circuit. You may have too much logic on clock paths, which may lead to excessive clock skew. You may need to go back and fix your clock distribution paths. You may have timing issues with asynchronous logic, which we did not cover, so don't worry about it at this point. Basically, the tool will hopefully provide you helpful errors. That's the key expectation. Via reports that will contain paths that fail to meet the timing. And it enables you to have a place from where you can start debugging. But unfortunately, as I said, these are not perfect, and don't rely on the perfectness of the tools as a designer. So you need to really know how your design well, and you need to really have a good understanding of timing if you really want to design a circuit that's really very, very aggressive in terms of timing. And we didn't even talk about power, right? We could even have a full lecture on power in a similar way, but I'm not going to do that clearly. Okay, basically, you may need to fix your timing errors. And to fix the timing errors, we already discussed this actually. Usually fixing the timing errors is a manual and iterative process, basically. You need to meet the strict timing constraints, and this could be tedious. You need to figure out where the problem is. The tool may point you to some direction that you need to go and fix what the problem in that direction is. You can later fix the problem, try synthesis and place en route with different options using the tool, different seeds, because tool, again, it does a random exploration. Usually, sometimes they can do, for example, Monte Carlo simulations, etc. As a result, they don't fully explore the space. So you may actually try to also guide the tool to actually explore some different space than it has explored previously. But again, no guarantees here. You're at the mercy of the tool. If you don't, especially if you don't know what you're doing, you're at the mercy of the tool. Okay, and then you can also manually provide hints, for example, to the tool, but now it becomes very, very tedious, right? And finally, I think you can manually optimize the reported problem paths. This is not a bad thing. You can simplify complicated logic, split up long combinational logic paths. That's always a good thing in general. And but the difficulty is fixing hold time violations is difficult, as we discussed earlier. So meeting timing constraints is essentially not an easy art and science in the end, because the tools are not perfect and humans are not perfect. And there are many ways of actually designing a circuit, as I showed you. Even the 4-to-1 multiplexer, we saw 3 ways, for example, early on. And they all have different timings, as we discussed, right? Okay, so let's go back to the fundamental principles over here. Clock cycle time is determined by the maximum logic delay we can accommodate without violating timing constraints. So hopefully that is clear. So good design principles help you in general. So in general, it's good to follow good logic design and architectural design principles. I'm going to talk about these, and I may actually introduce them later when we talk about microarchitecture. We're taking a little bit more time than expected, but that's okay. I think you can watch this lecture later on, and these are, as I already said, this is not going to be on the exam anyway, if that's what you're worried about. But these good design principles are really important in general, I think, when you're doing any kind of design. So basically, one important design principle is critical path design. You really want to minimize the maximum logic delay as much as possible without wasting things. This maximizes performance, right? And then you can decide, okay, whether I really want this or not. That's a separate issue. But critical path design is a good idea so that you maximize your performance as much as possible. Balanced design is another design principle. The idea here is to balance the maximum logic delays across different parts of a system. For example, between different pairs of flip-flops. You have this 2 flip-flops and you have some combination logic. And you have another set of 2 flip-flops and you have some combination logic. A balanced design balances the maximum logic delay across all of these different parts so that none of them is really a big critical path. And to be able to do that, you have no, basically this ensures that there are no bottlenecks. And it also minimizes the wasted time in any path in general. So balanced design is actually good for efficiency as well as not having bottlenecks in your system. And the last part is bread and butter design, as we like calling it. And the idea is to optimize for the common case, but make sure that the non-common cases do not overwhelm the design. So for example, if you have a common input that's going to be applied to your sequential circuit, maybe you should really optimize that path, because if you know your circuit, for example, if you know that some input combination never happens for whatever reason, then you can say, oh, I'm going to guarantee that this input combination never happens. And you can eliminate that from the consideration of the timing, for example, and you can optimize your circuit with that in mind. And this may actually now maximize your performance for the realistic cases, right? And this is really the common case design, and you may handle the non-common case in some other way. This will become more clear when we talk about microarchitecture 2 weeks from now as well. But if you actually follow these good design principles, these also help with meeting the timing constraints in a global level in your entire system, and also by minimizing your critical paths. Okay, we talked about a lot of interesting things, but hopefully you learned a lot about timing. Just to recap, we talked about timing in combinational circuits, sequential circuits, and circuit verification. The last part of the course was really about functional verification mostly. And we did talk about timing verification a little bit, but timing verification is really, we didn't really go into as much detail in terms of the testing of the timings and verification. With that, I think we have now covered the timing lectures, over timing and verification lecture. And with this also, we have covered essentially the digital design part of the course. Remember, this course is really digital design and computer architecture. So it's a broad course that covers digital design and computer architecture, and we're done with the digital design part. Next week, we're going to start with the computer architecture part, which is really the instruction set architecture and von Neumann model.